Let's go through this test that you attempted yesterday. There's the test. Let's do question 1 first. In question 1, it's a typical tensile test, and the results are force versus extension. However, the first question asks you to plot the stress-strain graph. So having a look at that, as you've done before in the examples, the first thing from the force and extension values which were given, you need to calculate the strain values and the stress values. Stress is force over area, so you would take the force in each case and divide it by the cross-sectional area. There was the specimen's diameter, so you worked out each of those and placed them in the table. The strain we know is extension over original length, which stayed the same. So for each of the strain values, you would take the corresponding extension and divide it by 0.2 and enter the value over here. Those are the values that you would then plot on the graph. And I've got stress on the vertical axis, strain on the horizontal axis, and these are the points that you would plot as accurately as you can. And then we've got to answer a few questions. The first one was the approximate stress at the limit of proportionality. So the stress where the graph ceases to be a straight line, which looks to be about this region over here. So go across and read off the value, and I made it to be somewhere around 42 megapascals. So we'll accept anything between 40 and 50. And then it was Young's modulus we had to find. Now remember, find a representative value, 2 values or 1 value, doesn't really matter, somewhere along this line, and then use the formula stress over strain, because we know that's what Young's modulus is. Find the stress at that point, find the strain at that point. One over the other gives you a value of 108 gigapascals. Okay, ultimate stress, you were told the breaking load, and you remember you divide that by initial area. Okay, so it came out to 115.67 megapascals. Finally, the elongation. Well, you were told that it extended 34 millimeters, and it was 200 millimeters long to start with. So that's 0.17 or 17%. In the second one, we have a bolt inside of a hollow tube, and there are washers either end. And they tell you that the nut is tightened until all looseness is taken out of the system. In other words, it's just starting to take up load. And then they tell you that the nut is rotated, half a turn. And remember, it's a 2 millimeter pitch thread. So half a turn means that this nut is going to advance 1 millimeter to the right onto the bolt itself. Okay, so the easiest way to understand this is to look at this little drawing where I've drawn the unloaded setup, where it's about ready to start taking the force, and then I have the loaded setup. Now remember that we are dealing here with materials that stretch under load. In other words, there's strain involved. So if you think about what's going on here, the same load is felt by the bolt and by the tube. The difference is the tube is tending to be shortened and the bolt is tending to be lengthened. And in fact, they are both changing slightly in dimension. And the easiest way to understand this is to pretend that you have drawn a line. Let's make it a red line. Here it is over here. On the bolt, 1 millimeter from where this blue washer's face is. In other words, the base of the nut is here, then there's the washer. So let's take it from here. Let's take 1 millimeter to the right and pretend that there is a red line drawn on the bolt there. As this nut advances onto the bolt, it will progress 1 millimeter to the right or onto the bolt. So that red line is going to end up being where this blue line is. Okay, now in so doing, the washer is going to move slightly to the right, and the red line is going to move slightly to the left. The sum of those two would be this piece plus this piece, and they will amount to 1 millimeter. Okay, so there's the loaded setup where the red line has now progressed to where the washer is. And the two dimensions are now identical. Let's look what the dimensions are. 150 millimeters became less by the tube compression. So 150 minus tube compression is the distance from there to there. At the same time, the bolt became longer. So it started out at 149 millimeters from there to there, and it's become a little bit longer. But now they are in fact the identical dimension. Look where they start and end, they're both identical. So 150 minus tube compression, that's this bit here, is identical to 149 plus bolt stretch. So the 1 millimeter, 150 minus 149, 1 millimeter goes to the left, and on the right we have bolt stretch plus tube compression. Now remember that E is PL over EA. Small e is PL over EA. So those two, that one plus that one, which is after all that plus that, must equal 1. Now it's a simple matter of doing the maths. There's the 1 PL over EA plus the other PL over EA equals the 1 millimeter. P, however, is common to both because they both feel the identical load. The one is tension, the one is compression, doesn't matter. They are numerically identical. So you take P out and you put in all the values for the one and all the values for the other. And you solve for the fact that P is 71 kilonewtons. Then you go back and work out the stress in each. And remember, stress is load over area. So that's the stress in the bolt, that's the stress in the tube.